If you need to add 87 plus 15, how do you do it? I bet asking this question to those of you watching this, there are lots of different ways that you are all doing it. Um, this next section, this next part of chapter 3 is 3.2, and it's all about addition and subtraction. You might be thinking, how much is there to talk about? There's a lot to talk about here. There are so many things that you might not have thought of before when you are asked to add or subtract numbers, different ways you can do it, different strategies, the different ways people think about it. I guarantee that there are some of you out there that are thinking, I would do it like this, and other people are thinking, oh, I would do it like this, and you might not even know that those are options. And it's not saying that one way is better than the other, but sometimes in certain situations, one approach might be better or more efficient or more optimal. It's really important to know all the different strategies and be able to link them with the appropriate situations. So that's what we're going to dive into in this next part of our chapter. So let's take a look at the overview and the terminology of what we will be looking at here. So there's a lot here, as you can see. We're going to start with a little introductory activity. We'll talk about some terminology associated with addition, like sum and addends. Look at different models for addition algorithms. What is an algorithm? Partial sums, left to right addition, scratch method, right? So different ways that people might do it. Then we're going to get into number properties. And these properties will also investigate in later sections in this chapter as well. The closure property, identity, associative, commutative, how these properties are they're so important that they have their own names, things we can do with whole numbers when we're adding. We'll talk about inequality of whole numbers, less than, greater than. Then we'll get into some models for subtraction, something we call an inverse operation. Different ways subtraction can be viewed. Difference, minus, missing addend. Again, you might not have thought of subtraction other than one of those in the past. Different concepts, takeaway, comparison, missing addend. And then how do we do mental calculations? A few different versions, approaches, compatible numbers, substitutes, equal differences, and the add up method. And then finally, we'll talk about approximation of sums and differences, using estimation, approximating by rounding, finding compatible numbers, and then doing front-end approximation. So all this is about just good old-fashioned adding and subtracting, but again, maybe not in a way that you have seen before. So here is your first little challenge, your little activity, your little problem opener. Okay. And again, by doing these, we're really setting the stage for what's to come. It's going to make you think about really important things. I don't want to spoil the surprise. So go ahead and do this problem. Use each of the digits 0 through 9 exactly once to obtain the smallest whole number difference. So you're going to take the 10 different digits 0 through 9 and put them in these 10 little boxes so that when you subtract, you get the smallest possible difference. Go ahead and pause the video and see what you can come up with. And also, while you do it, think about how you're thinking through it. So what did you come up with? And more importantly, how did you think about it? We had all those problem-solving strategies we talked about in chapter 1. What did you do? For me, I used a little bit of the guess and check method, but as I thought through it, I considered some things. And our goal was to get the smallest whole number difference, which means because of place values, our place values at this end are bigger. They have a much bigger value than the place numbers at this end. So I'm okay with when I subtract, I'm okay if these numbers end up a little bit bigger down on the right, but I need these numbers up in the front left to be very small because, again, we want the smallest possible number. So I would love it if these numbers out front could be very small. So as I started to think through this problem and do it myself, the first thing I tried was starting with a something like this. This was my first combination of numbers that I tried. 20,000 something minus 19,000 something, right? That was my first thought. Could I get the difference between the thousands up here to be just a 1, and then see what happens over here? And so then once I put those down, I thought, all right, well, what if I use small numbers on the top, like the remaining small numbers of 3, 4, 5, and then the biggest numbers like, but in descending order, 8, 7, 6, right? So I use my bigger numbers on the bottom, 9, 8, 7, 6, starting with that 1, and then the 20, and then increasing with the bigger numbers, 3, 4, 5. So once you do that subtraction, what you end up with is a difference of 469 when you subtract this. I won't worry about how we do it or the algorithm, but that's the first thing that I came up with. That's not the right answer, but that was the first thing I tried. So then I started thinking about it more, and I thought, well, what I picked here were numbers that were the 2 and the 1. Those ended up smaller numbers. And I thought, well, what I'd really like is to see now, can I shrink this, right? Can I get that hundreds digit, right? Because I got it less than 1,000, which was good. But can I shrink that hundreds digit somehow? Can I somehow get these two numbers closer together? That was my thinking there. So I thought to myself, all right, could I possibly get these numbers maybe closer together, or at least the numbers themselves, but these numbers, that's what really matters. 203 and 198. If I just focus on those, because those are 5 apart. So it led me to my next guess, which was this. What if I try a bigger numbers out front, like 60 and 59? So these first 10,000 digits are sort of more toward the middle of my set of numbers, 60 minus 59, and then plug in the rest to follow. So I tried my 1, 2, 3, and I tried my 8, 7, 4. And so as soon as I did that, the first thing I noticed was that, oh, I've still got a difference of just 1 out front between 60 and 59. But here, when I add that third digit, 601 and 598, there's only a difference of 3 there. I'm like, oh, that might be more where I want to get to. When I subtracted those, I ended up with 249. And I'm thinking, okay, I think I'm onto something here. So the goal was, rather than have these numbers out front at the very beginning of my number, I'm thinking, could I utilize those smaller 1s and 2s somewhere in here better? And so then I thought, all right, my goal is to get these numbers out front more toward the middle. And so I said, what if I use 50 and 49 rather than 60 and 59? And then let's fill in the other 3 numbers. And I used my 1, 2, 3, and I used 8, 7, 6. And immediately I compared it to this, and I thought, okay, I've still got my 1, 2, 3, but now instead of 8, 7, 4, I have 8, 7, 6, which moves these two a little bit closer together, which is going to lead to a smaller difference. When we subtract that, we get 247, and that is the smallest possible difference using those 5 numbers without having them repeat once. So 247. So this was our subtraction problem that we ended up with. 50,123 minus 49,876. Now you might have thought about that a little bit differently than I did, but the point was we had to start thinking about, to solve that problem, how do place values relate to each other, and how do we actually do our subtraction? Okay, we're going to get to some of those methods later as we go. But again, that's meant to just get you thinking about these topics right away. So the first thing we're going to do now, or I guess the next thing, is define something. We've been talking about, in this entire chapter so far, whole numbers. And I wanted to make sure to just talk about the definition of whole numbers, because we're going to use this definition. We're going to use the term whole numbers to define some things in a minute. And I want to make sure we're all on the same page. here's kind of a formal definition of what whole numbers are. Whole numbers, it's the set, they're the set of whole numbers is W equals, and then we see 0, 1, 2, 3, 4, dot, 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 the ellipses. So whole numbers start at 0 and they work their way up counting by ones. Note that 0 is a whole number, but it is not a natural number. So a natural number is often what we call counting numbers. And so natural numbers, as you can see here, are a subset of whole numbers. Whole numbers include 0, but natural numbers don't. So that's an important distinction. I want to make sure we talked about that before moving too far on in this chapter. So again, whole numbers are 0, 1, 2, 3, 4, etc. Natural numbers, 1, 2, 3, 4, etc. So the only difference is that number's 0. Okay, so now what we're going to do is introduce another definition, okay? And it's going to be, what does it mean to add whole numbers? You probably know how to add. You kind of have a concept in your mind, but we need to come up with a formal definition, right? We know that if we have 2 rocks and we add 3 rocks, 2 plus 3 gives us a total sum of 5. And so we start to think about this in terms of putting sets together. Remember the idea of adding sets or taking the union of sets? Taking 2 sets and their union is often used to define what addition actually means. So what I'm going to show you now is the formal definition of addition. So take a moment to just read through this. Pause and read through this. Maybe read through it a couple times so it can start to make sense to you. So how are we comprehending this? It's saying that R is a set. If set R has R elements, so we got a set over here, going to call it R, and in it is some number of elements, right? There's a number of elements in here, which is going to be R, right? It's going to be a number. And then there's some other set over here, S, and it's going to also have some elements, some number of elements. And it's important to also note that R and S are disjoint. You remember what that means? It means they don't have anything in common. They don't have any elements in common. That's actually a really important part of this definition. Then the sum of R plus S, which symbolically we write like that, lowercase r plus lowercase s, is the number of elements in the union of R and S. If you take R union S, you're going to have some set with a number of elements, and it's going to be however many are in the set of R plus S, lowercase, right? So we start to define a process, a mathematical operation in terms of sets. And we also see another term, addends. So this word addends is the numbers that we are actually adding, okay? The numbers R and S are called addends. Okay. So it is so important that those sets are disjoint, that they don't have any numbers in common. If they did have numbers in common, then you couldn't determine the total number of elements in 2 sets by simply adding them. And let me show you what I mean by that. We're going to look at a scenario, all right? And to sort of make sense of this. So I'm going to read this scenario. There are 8 people in a group who play the guitar and 6 who play the piano. These are the only people in the group. There are 3 questions that I want you to consider. Pause the video and consider these questions. 1, what is the minimum number of people in this group? 2, what is the maximum number of people in this group? And number 3, in which case, question 1 or question 2, can the answer be found by adding the number of people who play guitar to the number of people who play piano? So I want you to take a minute and think about those questions. Pause the video and then come on back. So what do you come up with? What do you come up with? So hopefully for the first question, the answer you came up with was 8. So why is it 8? Well, you could have a scenario where there are 8 people, 1, 2, 3, 4, 5, 6, 7, 8, 8 people, and all of them play the guitar. But 6 of them, these 6 will say, play the piano. So there's the group that plays a piano is a subset of the group that plays the guitar, right? So everybody plays the guitar, but only 6 of those people play the piano. So that would mean there's 8 people in the group. That's the minimum number. The second one is, what's the maximum number of people in this group? Well, if you're trying to find a maximum number of people, you're really looking at 2 sets, one who plays the guitar, and I'll overlap these, and I'll say the other one plays the piano, but the 6 people who play the piano, 1, 2, 3, 4, 5, 6, don't play the guitar. None of them play the guitar. And the 8 people who play the guitar, 1, 2, 3, 4, 5, 6, 7, 8, none of them play the piano. So in this case, we would have to add the 8 plus the 6 to get 14. So in this case, the maximum number of people would be 14. So in which case can the answer be found by adding the number of people who play the guitar to the number of people who play the piano? It's this second one, right? It's when we're trying to find that maximum. So that demonstrates that idea of our sets have to be disjoint, right? They had nothing in common, no elements in common, if addition was going to state what the sum is, all right? So moving on from that definition, let's talk about what an algorithm is. And we're going to look specifically at addition algorithms. And so an algorithm, you may have heard this word before, is a step-by-step procedure for computing something. You do step 1, you do step 2, you do step 3, you do step 4, and then you get your answer. Now, addition historically has been, you could state that the algorithm for addition looks something like this. The algorithms for addition involve 2 separate procedures: A, adding digits, and B, regrouping or carrying when necessary so that the sum is written in positional numeration. That's like the addition that you learned way back in elementary school, probably, where you stack numbers on top of each other. We use the word carrying a lot of the time, and that probably originated from a time when actual physical chips were moved and carried to the next column. Maybe you're using base 10 numbers. Now, there are many models for providing an understanding of these addition algorithms, and we're going to start by reviewing something we learned in the previous section, which was that bundle of sticks method. Remember, we talked about bundles of sticks. And so what we're going to do is we are going to add 2 numbers together. We're going to do a little addition, 26, and we're going to add 38. So we're going to take 26 and we're going to add it to 38. And so what I'm going to start with is I'm going to show you what the initial bundle of sticks, I was saying bundle of sticks, what that visual might look like. And it would be this. So take a look at that. Notice you have 2 bundles of 10 and 6, and 3 bundles of 10 and 8. So there's 26, and we're going to add it to 38. Now, in our traditional addition algorithm, what we would do is we would have a tens column, and we would have a ones column, like this. And we would say, all right, we have 2 and we have 6 for the number 26. And we're going to add that to 3 in the tens column and 8. We would add and we would often draw a line. And so here's that first part where we're going to add. So if we add 6 plus 8, I want you to really think about what's happening with that bundle of sticks method, right? What's happening with the bundle of sticks? Well, 6 plus 8 is really 14, right? It's this 6 plus this 8. But one of the things we learned in the previous section is this idea of regrouping using a minimal number of minimal collection, right? So actually, what we can think about is these 8, think of these 8 sticks here. And if we group them with 2 of the sticks there from the top 6, what do we end up with? Well, that's a 10, which leaves us with 4 individual sticks left over. So when we regroup or do some carrying, that's what's happening. What we're typically going to do is we're going to write the 4 here and we carry the 1 up there. But it's so important that what early students who are learning this understand is that that 1 is really representative of this grouping here, that 10, okay? But we put a 1 in that 10's column. And this turns into another one of these, right? These 10 turned into a full bundle of 10, which gives us 1 plus 2 plus 3, which is 6. 6 groups of 10. 1, 2, 3, 4, 5, 6. So our answer is 64. So again, there's an idea of how we use a visual and a model to show that, okay? And that is one of those, again, content standards, going back to our Common Core. Students in grade 1, first grade, understand that the 2 digits of a 2-digit number represent amounts of 10s and 1s, and that 10 can be thought of a bundle of 10 1s, right? That's what we did right there. Moving on to another statement by the National Council, the Teachers of Mathematics. What we just looked at was those bundle of sticks method. And right here, right, students should design their own algorithms and discuss, compare, and evaluate them with their peers and teachers. This is something that I do even in my college classes when I'm teaching students, teaching adult learners, things they might not have learned even in elementary school or middle school or high school about ways you can view numbers. Pose a fairly simple thinking question. Remember the one I gave you at the beginning, 87 plus 15? And then you ask people to share how they did it briefly. And then you ask as many different ways that people thought of a problem. How do they do that? This is often when you first start doing this, often it's represented in dots, right? You might say, put an arrangement of dots, something like this. And you might ask students to quickly add how many dots there are, and then tell you how they did it. And a lot of times, some students will say they looked at groups maybe like this, or maybe they looked at groups like this, or maybe they looked at groups like 6 plus 3, right? Like students come up with all sorts of ways to see numbers, and doing something called a number talk is a way that students can design their own algorithm, discuss, compare, and evaluate, right? Having those discussions where students share their own thinking is crucial for them to understand the best ways and other ways and new ways to think about problems. So next, we will just introduce another piece of terminology called partial sums. Partial sum, just so we are familiar with all the important terminology here. And the partial sums were really what we did in the previous example, where we were adding the ones first. 6 plus 8 is 14. That's a partial sum. We got a sum of the ones column, but we weren't done, right? And it involved regrouping, as we talked about before. So that's the idea of a partial sum, where you kind of work in different parts of the problem, get different sums, regroup some things, redistribute certain values to different place values. So let's look at a couple other situations of how those partial sums might look. So here is the number 345, and we're going to add that to 278. So the way that I showed before was where you might carry the one from one column to the next. So another way you could add these numbers is start with the 5 and the 8, which are in the ones column, and say, all right, well, I know that's worth 13. And so then that one just carries into the tens column here. Then you go to the 4 to the 7, and you say, okay, 4 plus 7 is 11, and you would write that here. Why would we write it there? Well, it's really 40 plus 70, which is 110. So it's always lined up with the rightmost column to where you're adding. And then you can go to the 3 plus the 2, which is 5. Really, you're in the hundreds column. And so you're adding 300 plus 200 to get 500. So you have to keep things in the proper columns. Once you've done your partial sums, those are partial sums, here, here, and here, then you add vertically with the remaining numbers, 3, 2, and 6 to get 623. So that's one way you can add those numbers like that. You might not have seen it done like that before. Here's another way. Let's still use 345 plus 278, except this time I'm going to kind of write it in a version of expanded form. So 345 is equal to 3, I'm going to write hundreds plus 4 tens plus 5. And we'll just say 5. It's ones. We'll just say 5. The same thing with 278. 2 hundreds plus 7 tens plus 8. So we're sort of seeing the written words of the place values. Then when we add, what we have here is, and you can do it from left to right, it doesn't really matter. I'll add from left to right here. We've got 5 hundreds plus 11 tens plus 13. Well, then we have to start doing some of this regrouping, right? And so what you might notice here is that you have a 10 plus a 3, right? And so that immediately can be regrouped here. And so we bring it down 3, and this would be, well, oh, look at that. There's a 10 plus a 1. This is going to shift over into the hundreds column. So we have a 10 here plus the 1 10 there. So what we have is 2 tens, right? There's regrouping happening here. And then this 10 comes over here and becomes a 100. So every time it shifts over, right, it becomes one of the next column. And so we've got 6 hundreds. So you can see this regrouping, right? This regrouping, it shifts over to be adding one more to the tens, adding one more to the hundreds when we regroup it. And then that results in 623. Okay, so all these different ideas, approaches, ways that you can see the numbers work based on their place value. Now, typically, I know the way I was taught was you always added this way, right? You'd add these and then these and then these. That's how I was taught. I think that's a lot of students are taught. But there's no reason you have to do it like that. Some children learn from reading. We read left to right. So some children find it natural to add in that direction as well. And there's nothing wrong with that. There's nothing wrong with doing your addition from left to right, as long as you understand what it means and how to develop some sort of notation that works for you. And so let's say we have to add 897 plus 573. Okay, so let's say we're adding those two numbers. So the first thing you might do if you want to add left to right is add the 8 plus the 5 to get 13. And then maybe you add the 9 plus the 9 plus the 7 to get 16. Well, when you do that, we're going to immediately add the 1 to the 3 to get a 4 and have the 6, right? So you had 16, but rather than carrying it and adding it later, we're just going to do it right away. Here's the 6 from 16, cross off the 3 and add 1 to it. And then we do the same thing with the 7 and the 3. 7 plus 3 is 10. So we add the 0 and make that a 7. And then we just bring all the numbers down, 1, 4, 7, 0. And there we go. There we have it. Right. So you're kind of doing an alternative version of your notation, but it's adding left to right rather than right to left, or rather than right. Yeah, you're doing left to right rather than right to left. In the early Hindus, later Europeans did this. They added from left to right traditionally, and we call this the scratch method. Why? Because you're scratching off the numbers and you're replacing it with its new version, right? As you go. And again, there's nothing that says one way is better than another. It's just they're different, and that's okay. So what I would challenge you to do is just this final problem here is we're going to take 694 and we're going to add it to 539. And what I want you to do is just try those using several of the different methods that we talked about. Kind of the traditional, what was the first one that we looked at? Maybe the partial sums, where you're just kind of bringing down each partial sum and then you add them all at the bottom, the expanded method, and then the scratch method. Go ahead and pause, try those 3 different methods. I'll keep going. So again, if we're going to take 694 plus 539, one way you might do it, 4 plus 9 is 13. 9 plus 3 is 12. 6 plus 5 is 11. They're stacked like that. And then we add those partial sums to get 1,233. That's one way, right? We're not even doing any carrying up to the top. We're just writing each partial sum individually. Another way is to look at it in expanded form. And you don't even have to write the words if you didn't want to. You could write it as 600 plus 90 plus 4. This would be an alternative. 500 plus 30 plus 9. And then you add. 4 plus 9 is 13. 90 plus 30 is 120. Or maybe you had 12 tens. And then 500 and 600 is 1,100. And then again, you can do some regrouping. 13 is 3. We move 10 of them over here to be 130. Again, I'm even kind of coming up with a slightly different version. Here we've got 130. Let's take 100 away and move it over here. Add it to the hundreds column, 1,200. And now we take what's left, 1,200 plus 30 plus 3, 1,233. Right? So you even have alternatives. The last one, 694 plus 5, 39. Maybe we want to try adding from left to right. 6 plus 5 is 11. 9 plus 3 is 12. There's our scratch method. 4 plus 9 is 13. Add there. There's our 3. Drop them all down. 1, 2, 3, 3. Look at that. So we have 3 different methods, all giving us the same solution. And again, the point is, it doesn't matter what you use. It doesn't matter which method you use, as long as the key is understanding place values. That's what it all comes down to.